me start. Hello, everybody. This is the third webinar I'm hosting here. The first was on parsing and the second on semantics of kind of how compilers see them. And today we are going to talk about evaluation. And this topic, especially for C++, is really important because in C++ you have to do a lot of compile time evaluations, and basically you can do anything in compile time, whatever you can do in runtime. Briefly, how this is going to go, I'm going to be telling you things, hopefully useful things, and showing you a lot of slides. And if you have any questions, put them in the chat. You have it right there in Zoom. And when we finish, I will answer any questions. Okay, so let's begin. My name is Yuri. I work at PVS-Studio. I'm working at a static code analyzer which deals with C++ code. And these are my sources of inspiration, kind of. So today's talk is about evaluation. So what is evaluation really? Well, let's say we'll start kind of easy and small. We have an expression like that. It's a binary expression with sub-expressions, and it looks good and fine, and so on. So this equals to 0. And how do we know that it equals to 0? Well, I mean, it's obvious. We as humans can easily calculate that. It's really a simple arithmetic set of arithmetic operations. But how does a compiler know? Well, last times we talked about ASTs and things like that. So this expression in the AST, or abstract syntax tree form, looks something like that. And well, this representation is really inconvenient, so let's make a better one. This is what, by the way, Clang will happily draw for you if you ask it nicely. So we have a syntax tree like that. To calculate what's going on there, we enter from the root and we start descending down. And that's basically your typical tree depth first approach, when you are recursing all the way down, then up, then different branch, and so on and so forth. So go down, we go down, and here we have a terminal node, which doesn't have any subnodes. And it's a literal, and we can calculate its value easily. Okay, the second one is this multiplication. Again, it's a binary expression, so we go left. That's a 3 there, and we go right. And now we are done basically with that sub-expression. So on our way back up, when we climb back, here we apply the multiplication operation to those two operands, and yeah, we get 99. Same here. That's 1, and now we calculate the right operand of that binary 1, and so get a 0 eventually because we climb back. We do 1 minus 1. Well, looks simple, right? Let's see how we could do that. Well, to traverse a tree, we need to have something, well, some class or a set of functions which implements that logic. I'm calling it the AST walker here. That's an arbitrary name, not a technical term really. Well, basically it's a visitor. what I'm talking about. So here's what our AST might look like in the simplest case. We'll check out only binaries and literals here because that's what the example is dealing with. In reality, well, there will be a lot of different nodes and different kinds of them. So I said the word kind. We have a kind. This is basically a tag which we apply to a tree node, which tells us what it is. And it's stored in the basic base node class. And now we can start inheriting from it. So let's have a literal and a binary, and these descending classes are where we implement interfaces, really. The base node will only have like an ability to ask, hey, what are you? Are you binary? What? Okay, so for binaries, obviously we need to have operands, and we have to have information about what operation to apply to them. And for literals here, we'll just keep strings there. Well, when we are parsing, we are dealing with a long text buffer where all the values of everything is stored, really. It's an entire file. So we can safely grab substrings from there and store them in our tree. And why we are storing strings? Well, because if you pre-evaluate values of AST nodes, you might run into issues, especially with floats, because the value in the string form, it will stay always the same. And if you like calculate a float from the string, you might get into calculation errors and irregularities there. And since we have a class hierarchy, let's also define some constraints. This is the setup phase, basically. We'll have a concept, really simple one, which just tells us that we are trying to use some class which is derived from the base node. And let's have a class visitor. We'll look at it in a moment. And here, this is an important part. As you can see, this last concept, visitable, what it basically does, it will be applied to classes that derive from the base visitor. And it will check whether or not the derived class has the visit method exposed. We'll see in a second how it works. Okay, so if you look at this definition, you will see the type name derived there. This is because we'll be using CRTP. If anyone doesn't know what CRTP is, it's translated into curiously recurring template pattern. And it is when your base class is templated by the derived class. So basically when you inherit from it, you specify that, oh, here I am inheriting from you. Okay, more setup here. This one will be used when we push pointers to nodes around. What it does, it respects const basically. So into our visitor, you can pass either a non-const node, for example, if you need to traverse the tree and change something, or you can pass the const node where you only read from the AST. And yes, this thing can potentially modify the tree itself if you so choose. And this is our entry point operator. I decided to make an operator here just because it kind of looks neat. And you call the visitor as a function. And returning to that concept we defined earlier to the visitable concept. In our base class visitor, we have the visit function, which accepts something like that. What it does is it takes your derived class, your really actually derived from the visitor, and it checks if this derived class has a function called visit, which accepts a node, a reference to node of this specific type, which will be inferred in the function call, then we will cast ourselves, this pointer, into the derived type, into a pointer to the derived type, and we'll call that visit function from our descendant. And if it doesn't, then we have like a dump visit function in the base, which will accept absolutely anything, and it will just do nothing. And we also have something called visit impl. This is where traversing of the different kinds of nodes happens. Like, for example, for a literal, we just go straight into the node. We just go straight visit it and let the derived class figure out what to do here. But for a binary, for example, this is what we do. So we take the binary expression node and we first go into the left operand, into that left branch, and then we go into the right branch recursively. So this tree visitor is recursive. Well, trees are recursive by nature, so it's a logical thing to do. And then after we have processed left and right subtrees, we go and look at the node itself. And if you are wondering what visit root is, well, here it is. It's just a switch case. What it does, it checks the kind of the node. A basic node comes to it, and it casts it to the descendant class of that node according to the kind, and it respects constness also. So if you have a const binary expression node coming into here, you will have a const just node, and it will be cast into a const binary expression. Let's see how it works in practice. Let's implement something simple, stupid, and useless, frankly. Let's say you want to, in your tree, for the entire program, potentially, you want to catch all literals, like every single number which is explicitly written in your code. And you want to do something with them. Let's call it a lit matcher, which stands for literal matcher, but anyway. So what do we have to do here? I'm omitting the public access specifier here, just so you know. The visit function you see is public in the descendant class. And the usage of that, as you can see there in inheritance part, it's a literal matcher, which is the name of our derived class. And we will deal with like const tree nodes because we are not planning on modifying anything. And this visit, let's say what it does is just posts a string from the literal, from each one. If we call it like that, so let's say we have that expression we looked at the very beginning, and we pass it to this visitor, well, we'll get that. So it will go 133, 3, 1 in the order the AST is built. And as I said, this is everything we have to this class. So any other node in our AST, which is not a literal, will be just skipped over. It will go into our generic visit function, which accepts everything and anything and does nothing. So this logic will actually work only on literals in this case. And this is kind of similar to what you could achieve with just virtual functions in your visitor. But I think this is better because, virtual functions can be slow. And also you have to either define them in the base class, all of them, or you have to define them in descendants. So you cannot have the base class really an abstract one. So otherwise you will have to go into the descendant and define everything. Okay, so that's what we can use to evaluate things using the AST, and let's look at it right now. So how would an AST walking evaluation work? We have an expression, we have the AST for it, and we need to traverse it and do things. Okay, well, so first of all, you will going to have a stack for evaluation, because the way it works, you go to a node, you evaluate its value, you push it on the stack, and next time you need to have some operands, like for example, for a binary expression, it's left and right, they're on the stack, so you first pop them and then use them in calculation and push the result back. Again, we will use the same expression we used before. So let's go. Well, first we descend all the way down to this first left operand of the expression. So it's 100, it goes on the stack. Next, the right operand is the multiplication. So 3 goes on the stack, 33 goes on the stack. We climb, and here, this is where multiplication is applied. So on our stack, we have 99 for the multiplication, so the right operand, and 100 for the left operand. And if you look carefully, you will see they are kind of backwards. So when we actually apply those binaries to their operands, we have to kind of pop the right one first and then the left one. We could change that by traversing the right branch first, but for binaries it would work, but it's not the way to go, so we'll have to just deal with it. We'll look at the right operand first. Okay, so this minus, of course, results in 1. This one also results in 1. And eventually we get a 0 at the end. Well, it looks really simple, and actually it is. It's an extremely simple thing if you're doing an evaluator to do. And probably it's the first thing which will come to your mind if you decide to I bumped into this a long time ago when I tried to create a calculator for arithmetic expressions, and it's really a natural way to go. But as everything kind of simple and easy, it has, well, some issues. Let's look what issues does this approach have? What issues can it potentially have? So issue number one is, believe it or not, logical expressions. So look at that nonsense. Uh, I know it's nonsense, and it's not nonsensical deliberately here. And let's look at its AST. So we have the logical operation at the top, because we need to look at it last. And those comparisons are its operands. And it's a binary expression. It's in no way different from multiplication, for example, in terms of how it's built. But if you look at it, it's a logical AND, but the left part of it is always false. Because 100 is never, no matter how hard you try, is never less than 1. And since it's false, we have, for logical expressions, we have the rule that they short circuit. So if you have a logical AND and its first operand is false, you will never evaluate the second operand. That's for C++, that's built in right into the language. That's how it works, and how it should work. And for logical OR, it's the opposite. If the first one is true, the second one is never evaluated ever, which is a good thing because it allows us to do things like check for some pointer for null, and then perform a logical AND and use that pointer to reference it somewhere. But if we just go recursively doing left, right, and so on, we will inevitably evaluate both operands, which we don't want to happen. Okay, back to the drawing board. How can we deal with that situation? So remember that visitable concept. We'll have to do another one. And that one is for previewing a kind of node before we do something with them. So as you can see, it requires the derived class to have a function called preview for the given type of the AST node. And it should return bool. And this function, how it works, it should return true if we actually want to process children of a node, and it should return false otherwise. And we'll do with that preview function the same thing we did with visit. So the default generic one will just always return true. So by default, we always descend into children of a node. And our visit impl, the thing where all the cool logic happens, it will start looking like that. So just if the preview return true, it will go into the operands, otherwise it won't. So let's see what the implications for that are in a derived class. Let's say we have a class called eval, which is an evaluator. And for binaries, well, it does the usual stuff. Remember, I said that the right operand goes first from the stack. So here it is. We first pop the right, then the left, and then we calculate the binary using the operation, which is actually there. And in preview, well, here we have kind of a bit of ugly logic. So this check, if the binary expression we are dealing with is not a logical operator, then we are done here. We just visit the expression normally without any additional checks. So it's just a calculation. But if it does have a logical expression, logical operator. So what we do, we call ourselves on the left operand first, and then we get its value, and then if it converts to bool, if it's true, and we have a logical OR expression, we have to return false because we don't have to go into the right operand. And if it's otherwise, if it's false and we have a logical AND, we also return false here. And otherwise, if it's not, well, false, and we have, well, you get the point. So we check the condition for this short circuit here. And if that condition does not work in this case, only then we will go again into the right operand and, well, calculate the entire thing. Well, it's not the ugliest thing in the world, but still it's kind of inconvenient. Issue is a more fun one, really. Let's say we have a function. So how do we evaluate function calls? Well, we on this, and then when we are done with that, we just recursively call ourselves on the function body and go traverse and evaluate that. And it's all fine and okay, it works, but consider this. Let's say we have an early return here and we return something else if the condition under which an early return is written is not does not apply. Our AST starting from the function body could look something like that. So again, we go do the usual stuff. We see the if statement and we go into its condition. So all is well here. We evaluate two operands, okay? And let's say this is true. So let's say we have like called to this function with 1 and 2. So 1 is less than 2. And so the condition is true. So we go into the if body. And eventually we get here. That's okay. But then we hit return. And this return, it needs to return us all the way back to the call site point. But the problem is we are in a recursion and we can be somewhere deep in a nested if statement or something like that. So we might not be even aware of how to go back from the point we are in. So if we just return from the current visit we are in, our visitor, it will continue to process the function body until the end, until it reaches the last statement there. And that's a problem because you don't want that to happen. If you hit an early return, you do not want to evaluate anything below it. So you have to skip it. Otherwise, you may run into some issues. For example, this return was there for a reason, like you have some invalid operation otherwise or something. And here, the solutions, potential solutions, are much uglier because you will have to probably set some state in your visitor and like when you hit return, you would assign some flag to, okay, status is returning and all other functions, all other visits will check this and exit, so it's ugly. It's not what you really want to happen. But this is, well, solvable still, but there is the third issue if you want to go the AST walking route for the evaluation, and that is, as usual, it starts with a simple and kind of benign thing. Well, here you see the textbook example of the factorial calculation. But let's first, well, let's check what is going to happen when we go and try to call it in our evaluator. So we will put the value of its operand on the stack. We'll go inside. Let's say we skip over the if, so we do not return 1 immediately. And eventually we'll go here. Again, we will calculate the function operand, push it on the stack, go into the function body to traverse it. We'll get here, and then we will get here and here again. And so we have a recursion, a classical recursion within our already recursing visitor here. So it looks basically like that. You enter the body, you visit the return, you visit the function call. It continues and goes on and on. And eventually, you will be in danger of a good old friend of mine, stack overflow. The problem here is you are recursively evaluating a recursive piece of code, and the depth of your recursion as the evaluator, not in the code you are looking at. It will grow with every time you enter the recursive call of the code you are evaluating. It will grow, and there's no real way to predict when you will crash if it goes on for too long. Without recursion, with low recursion depths, like let's say we try to calculate the factorial of 3, it's not a problem. But if it goes long enough, you will crash. And the saddest part of this is that you do not even know when it's going to happen. You could try to limit the number of calls, like the depth of recursion. That can be done. But the problem is you don't know the number, and it may differ for different functions. And even if we write the same factorial function in slightly different way, the consumption of stack memory of our own recursion functions will change. So yeah, that's a problem. And as far as I'm aware, there's no good way to even determine if you have enough memory on the stack right now at any given moment. There are some ugly ways, but there's no good way. Well, now in principle, you could, of course, traverse the tree without recursion. That's possible. But this has its own issues. Like you need additional memory, you need to manage a stack or a queue depending on whether you want depth first or the breadth first traversal. So it's not an ideal solution, but you could. But actually, there is a better way to deal with this evaluation thing altogether. So if you tried reading books or any literature on parsers and stuff like that, on compilers, you might know about the IR, or intermediate representation. And what it is, we'll look at it at a moment, in a moment. Also, what I want to say here is if you are using a compiler which has LLVM as its backend, you can ask LLVM to print out the IR, and it's kind of fun sometimes to look at it and see what different pieces of code become. Okay, so for our factorial function, the IR will look like that. Well, it's a big thing, really, kind of. And if you look at it, you might see similarities to the assembly language. And that's not a coincidence, because the IR is an assembly-like thing, but it's structured a little bit differently than a real assembly code. But the idea is the same. And if you look at it again, you might see those kind of labels. So you have entry, if then, if and, return. And if it reminds you about something, that's probably not a coincidence either. Because those parts of code between the labels, they form the control flow graph of your program. So in our factorial, we have something like that. So after entering the function, we have two ways to go. Well, two branches, because we have an if statement there. Both those branches do something, and they eventually converge into the last piece of that control flow graph, the exit node, which returns a value. And this structure, by the way, solves our early return issue quite nicely, because we always have just one return at the end of the function and never more, and we are guaranteed to have one. If the function returns nothing, we will still have a return void instruction at the end. Let's see how it's structured inside. So in IR, we have modules. Modules are kind of big logical chunks of code, and they can incorporate data structures, for example. For data structures, we just have a layout table, basically, of a class with just data members. It can have global objects, like if you have a global variable outside any function, the module itself will have it. And the main thing modules have are functions. And there can be any number of functions there. And what's interesting for global objects, if you have initializers for them, like let's say you somewhere in your CPP file, you write int a equals 42. This 42 is also a function in IR. The object itself will be initialized with via function call. So we don't have any instructions there, only functions. Okay, the function is what we just saw. It's like it has an entry block and it has a terminal exit block, and any function is guaranteed to have at least the entry, which can also be an exit if it doesn't have any branching. So if your function it doesn't do ifs, it doesn't do switches, ternary operators, logical expressions, and so on and so forth, you will have just one entry block. And in between, we have that arbitrary kind of control flow graph there. where we can have any number of basic blocks. These blocks are called basic blocks, by the way. Well, but they all follow the same principle. Any function follows the same principle again, is that one entry, one exit. So they start branching all of those blocks. They start branching from the entry always, and they converge at the exit. And basic block, it's basic. It contains just instructions. So it goes like that usually. You have an instruction, 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 a sequence of instructions, and the last instruction is always a jump to a different basic block in your control flow graph, or it's a return from the function. And this structure is linear. So we go top to bottom. We might jump somewhere, but we are still going top to bottom. In things like loops, we can go back, like loop back to where we started, but still, all the instructions in a function or in the entire program, really, they can all be like a constant string of instructions linked to each other. And basic blocks are, well, they're mostly just labels to differentiate between places where this specific instruction is found. And an instruction has an operation code and operands. And as I said, there is a sequence of them, like string. So it's a doubly linked list, basically. Well, instructions itself is kind of a doubly linked list node. So you know the next one, you know the previous one, and you can, if you have one instruction, you always know what's before and what's after. Okay, let's see how an evaluation works in this scenario. And for that, we'll use, well, we won't be using boring thing with just one entry and linear expression thing. We will use a logical one, logical expression. We'll use a logical expression, which means that we have a short circuit here. And at the right, there's what the IR for that might look like. It's not an IR you can get from like LLVM. It's just loosely modeled after that, because the LLVM's IR is more loaded with stuff. So I kind of made my own version for that, but the principle is the same. So again, you see a function, you see basic blocks, you see instructions, and you might wonder what these are. As you can see, every instruction has a result placed into something like a variable. Well, those things are virtual registers. They serve the same kind of purpose as registers serve in assembly, in that you keep values in them. But as you can see, every time we have an instruction which has any kind of result, we create a new register for it. That's because here they follow the SSA annotation, or single static assignment annotation. What it means is that any assignable thing, like a variable, can only be assigned a value once. So you can never overwrite a value in a virtual register. It's just assigned once. And this is mainly for data flow analysis and optimizations, because if you have SSA, it becomes much easier to reason about things like, for example, dead stores, when you save a value into a variable and never read it. Or if you save a value into a variable and overwrite it right next to that assignment. So using SSA makes such analysis much easier, and not using SSA really makes it a nightmare, frankly. Okay. As I said, virtual registers, they're used to store values. And you can do it kind of differently. For each function, you can allocate like a vector where every register has an index, and you use just those indexes to keep values in that vector. Or you can use a hash map or something, or you can just store values right in the registers. It depends on how you implement the registers themselves. So it doesn't really matter here. What matters is that for the entire duration of a function call, you keep track of all values of every register, and you clear them when you exit. So it's not as efficient in terms of used memory as our evaluation stack was, but it has its own benefits. In IR, we don't have recursion. We go instruction by instruction in the linear fashion. And so we have a big loop, like which goes on until we tell it to stop. And we have an instruction pointer. Same thing basically as machine code gets executed. So let's say we call this function with a equals to 100 and b equals to 10. This is what the caller function will put as our entry values, as our arguments. And we start from here, right from the first instruction of the first basic block of a function. And we are going to be tracking the last block we were in. Basically, we will be tracking the block we came from. Right now, when we get into the entry block, since it's the first and we've just called the function from somewhere else, last block will be empty because we didn't come here from a different basic block. So nothing is to store them. Okay, so this load will just load the value of A. This will load the value of B. We will store them along the end, along the way, along the end. Okay, so here we have the comparison. What it means is, it means compare SLT means signed less than, because we have signed values here, signed ints. And we compare those freshly loaded values. And since 100 is not less than 10, CMP is false. And this one is a conditional jump. Depending on the first operand value, we jump to different basic block. If it's true, we go to the end block, and if it's false, we go to the right-hand side block of that logical expression. It's false. CMP is false, so go here. I'll just omit the loads. They work the same, but take note that whenever we use a variable in different basic block, we always load it first, because it could have changed somewhere else. So we do not reuse previously loaded values in a different block. We just load a fresh value from the variable. Anyway, that's an equality comparison. 100 is not equal to 10, so it's false again. And okay, here we have an unconditional jump to the end block. And this one is an interesting, and it looks kind of weird, right? So what in the world is that? Well, this is how different blocks of branching paths converge. It's a phi node. And what it does is its value depends on the block we came from. So what's written here, if we came from entry, the value of the entire instruction will be true, because we have a logical OR expression, and in the entry, we evaluate its left part of the logical OR expression. And that's our short circuit here, because if the left part of the logical OR was true, then we just go to the end. We skip everything in between. So we skip the right-hand side block. And if we come from the right operand of our logical operator, then the result of that thing will be the value of the phi node. And also, as you can see, our last block here is the RHS, or right-hand side block, because we came from there. And so this is the resulting value of our phi node. Well, phi nodes really are for, again, for ascending analysis, for optimizations mostly, but in evaluations you can still use them. Well, you have to. If you build an IR for some function, you will inevitably have them if you have like branching. Okay, and so our register 4 equals to false, because we load CMP1, which is false. And here we can just return it. And our result of the function call will be also false. So hooray, we've calculated a short circuit without any need for recursing, previewing nodes, and so on and so forth. This is one convenience of having an IR in your, or let's say you're doing an interpreter or something. But the other benefit of IR is that you can optimize it. You can't really optimize the AST. Well, you can try, but it's going to be inconvenient, really. And for the IR, optimizations work better if you want to optimize some code for calculations. I'm not going to dive too deep into optimizations because it will go out of scope of this talk really fast if we try to do it. I'll just show you how constant propagation might work. And what constant propagation is, well, we'll see in a moment. So a simple example, again, let's say that we have a function and everything that function uses is known. Every value is known. Nothing comes from the outside. And no global variables are touched. We just declare things here and do something with them, assign them, initialize, and so on. And note that this function is not, it doesn't have a word const anywhere. So our variables are true variables. They are modifiable. Okay, let's look at the IR. Well, it really is no different than the previous example, except you have two allocations as the function starts, because we have two local variables and we allocate them in the entry block. And all allocations always go there. They go to the top of the entry block. They are first instructions in any IR, because you need to know how much memory on the stack you have to pre-allocate when you are executing functions. You have to know it beforehand. You cannot kind of do it on the way. Well, you could, but it would really harm your ability to properly evaluate or optimize that thing. And also note that the first store instruction, it's the third one, like in the entry block, it says store 42 into A. Why 42? Because 21 times 2 is 42, and we are not going to bother creating instructions for literal expressions. So here, when we generate the IR, we have to always check if we traversed some piece of AST, evaluated kind of its operands, and we have a constant, well, a known constant, not a variable value or anything, like we have literals. We just do not create instructions for them. We just pre-calculate them and put them into our IR. It saves time. You could actually just create a couple of instructions here, additional ones, like could do multiply 21 by 2 and get the results and put it into the store, but it's not necessary. Okay, so if we evaluate this function, we will get, like, remember the previous table, it will be like the same with different values, because the function really is the same as the previous one. But what we can do, since we know that the function returns a known value and it does not take anything from the outside, and it does not touch any global state, well, we know this function is pure. And not only is it pure, but it does not depend on anything. So it's the prime candidate for optimizations. Now let's see how it goes. Well, I'll get rid of those allocations and store. I will start with the load into 0. And by calculating like previous instructions, we know that the load from the A variable will always be 42. So our 0 is 42. Then we can put this value into the subtraction, and we can remove the 0. The previous instruction we can remove completely from our IR, because it is guaranteed to result in a constant expression. Why have it? No reason. And since we are using the SSA, we are sure that this 0 will never be assigned to anything again. We can just remove that 0 register. Okay, so subtraction, that's trivial. We can always subtract 1 from 42. So our register 1 is now also known. And again, as you see, instructions removed from the IR here, they will be actually removed if you do that. And we continue. So here 42 is not less than 41. So it's false. And jump on false goes into the RHS block, which will do. Again, I'm omitting those loads. We kind of just, we are still keeping like values for everything, but we are modifying our IR as we go. Okay, so this CMP1, 42 is not equal to 41, so it's false again. And we have an unconditional jump. And every basic block, when you see a jump or return, it means that the basic block is done. So it's the last instruction, and it can only be the last instruction of a block. So here we jump, we substitute false for CMP1, and well, again, fine node. We came from the right-hand side, so we can assume that the entire instruction is equals to false. And here's what our function becomes. With a set of linear steps, when we just substitute previous values into instructions, and we go and go and go and go and go until we have nothing else to optimize, until we have like reached the return. Also, yeah, that is what this function really is. And if we take this idea further, whenever, well, we can mark it as a pure function with known value, blah, blah, blah. And when we see a call to this function anywhere in our program, we can just safely replace it with just the value of false. So this constant propagation thing, it can be really interprocedural. And the nice thing about like IR is, well, you generate it for every function, and you know, like in C++, you can call a function which has not been defined yet, but you cannot like reason about it. You don't know its body, and it should be there for the linker. Well, in IR, every function which is in your translation unit will be accessible. Its body will be accessible to you no matter when it's called, so you can actually do those optimizations if you really want to. And well, let's see, that's all for, well, kind of like we touched on the optimizations briefly, but as I said, it could be really, really a long talk if we did not do it briefly. And back to recursion. Well, what happens in recursion again? You probably guessed already. So we are not recursing ourselves. So we are not in danger of Stack Overflow or anything. And here you see, by the way, just small piece of the factorials IR. It's just the first instruction and the function call. So it will be easier to show what happens. So we are in a big loop. Our caller function somewhere sees that factorial is called. Okay, so we are on the caller stack frame. What we do, we allocate a stack frame for the first factorial call. We prepare arguments for it, and we enter first frame of the factorial. Then we reach this call here. And here thing happens. We create a new stack frame for the next call, and it goes on and on and on and on. Those stack frames are allocated on the heap, probably. So the only danger you're in is to run out of the heap memory, which could happen. But the nice thing here, since you are not eating up your own call stack of your own evaluator, you don't have to worry that you're going to crash because of recursing too much, because you're not recursing. So what you can do is you can set an arbitrary restriction. For example, if you reach some stack frame deep into the function call stack, and it exceeds a limit you set, and this limit could be arbitrary. You can actually set whatever you want. Like you can set 1 million. Doesn't really matter as long as you have memory, as long as your computer is alive. Oh, well, we will still get a Stack Overflow, kind of, but this Stack Overflow is gonna be the stack call stack of our evaluated function will kind of overflow, and that's an artificial thing. So we are fine, but we say, hey, the limit reached, so it's kind of a Stack Overflow. We can report it safely and just bail out of the call. So we don't have to continue. We just can break, I don't know, from the loop entirely, and or set our instruction pointer to the initial place where our function was called and set a flag that, okay, an error occurred there. And well, the last thing we'll take a look at is how like real compilers do that. So again, this is our factorial. It's constexpr right now. And why is it constexpr? Because we are going to feed this nonsensical stupid code into Clang. As you can see, factorial of 1,500, well, pretty much it's guaranteed to be too much. Well, you cannot calculate a factorial of that number realistically in terms of the unsigned int. It's impossible. But let's see what Clang has to say about it. Well, it complains that the constexpr evaluation exceeded maximum depth. So here's what happens there. It counts the calls, and if we go past 512 calls deep, well, it's an error. Well, it's not really an error because our constexpr function in this case will be just postponed into runtime. So Clang will just generate the IR, and this IR later will be probably optimized by LLVM, and it will be turned into binary code, but still, it refuses to evaluate it at compile time further. By the way, I wonder what would happen if we had a const eval here instead of const expr. I didn't try. Probably it would be a compiler error, like again. And okay. And this is really all what I had to say today. So thank you. We are done.